Section 3 deals with finding real roots of a polynomial function. To begin with, first though, we must understand the process of using long division to find an answer. If you recall from last year, long division, the x plus 4 is your divisor. It belongs on the outside of your division symbol. The 2x to the 4th plus x cubed minus x plus 5, that is your dividend, and it goes on the inside. So you write 2x to the 4th plus x to the 3rd, and since there is no x squared term, we leave a space for it, and then we'll put minus x plus 5. You can also in here write a 0x squared term, because the dividend should be written in descending order of the exponent, just like the divisor should be. Then once you get to this point, then all you have to do is figure out what multiplied by just the first term gets you to the first term in the dividend. And in this case, x times 2x to the 3rd is going to get you 2x to the 4th. When you write this number up here in your quotient, then you multiply by the entire divisor. And so this would become 2x to the 4th plus 8x to the 3rd. Now then, at this point, we subtract this entire polynomial, and 2x to the 4th plus x to the 3rd, subtracting this, that would become 0, and x cubed minus 8x cubed is going to be a negative 7x cubed. Then you're supposed to bring down your next term. Well, there is no 0x squared, so then you would bring down a minus x. And again, you would go from first term into first term. X times what is a negative 7x to the 3rd? That would be a negative 7x squared. Multiplying this by the divisor, you would get a negative 7x cubed minus 28x squared. And so actually we did not need to bring down the negative x yet. Then going through and subtracting, and that's 0, and 0 minus a negative 28x squared is going to be a positive 28x squared. And then minus x is our next term that we would bring down. Continuing on, now what times x gets you 28x squared? Well, that would be plus 28x. And 28x times x plus 4 is 28x squared. Plus 112x. Draw our line and then we'll subtract again. And it's 0 and a negative 113x. Bring down our last term, the plus 5. And then complete the problem by figuring out what times x gets you a negative 113x. And that would be minus 113. And 113 times 4 is a negative 452. And then again, subtracting all of this, that will become 0. And this will be 5 plus 452, so 457. And then you can write the remainder as remainder 457. Or you can write it as a fraction and put 457 over your divisor. Either way is fine. Now then, you will also get some, and actually in that last problem you could have done this. If the divisor is a binomial binomial of the form x plus or minus b, you can and should use synthetic division. This is the divisor, and if it is in this form, x plus or minus some value, then you can use synthetic division. And remember, with synthetic division, you add down the columns, then multiply. And so you draw an upside down division sign, or a big L, however you want to look at it. And you do the same thing. Since this is your dividend, those numbers go on the inside. All you need are the coefficients. So it's 2, 1. There is no x squared term, so we need to put a 0, then a -1, and a 5. The integer on the outside is this one, but it has to be the opposite integer, so a -4. And then you go through the process of adding down and multiplying. So 2 plus nothing is 2. That would be a -8. Then we get a -7, a positive 28, 28, -112, and then a -113. Finally, 452 and 457. And this is the remainder. And this is the quotient. And the quotient then would be 2x cubed minus 7x squared plus 28x minus 113, remainder 457. Whatever your initial polynomial started with as far as the degree is concerned, your quotient, when you divide by something like x plus or minus some number, will start at 1 less than the degree you had to begin with. Now then, when using synthetic division, you have numbers here, you add down, get a number, multiply, then add down, multiply, add down, and continue on until you get to this value here at the end. That value is your remainder. And so because there is a 3 here, we know that f of 3 equals whatever number is in here. So for example, if you went through this whole process and got 32, we would know then that f of 3 is equal to 32. If, by chance, you get something where it turns out to be 0 at the end, well, first off, we would know then that f of 3 is equal to 0. We would also know that since it is 0, 3 would be a root of this polynomial function, or a 0 of this polynomial function, or you can call it an x-intercept. And we would also know that x minus 3 is a factor of that dividend. Now, in order to find some roots to polynomial functions, you have to go through that whole process of doing the L thing, going through and figuring out and finding those that make 0 here. Well, to help you with that, there are some tests that you can do prior to starting to help you reduce the number of integers you have to actually try. Initially, it's infinite integers that you would have to try, but the rational zero test first off tells us that since the degree is 4, there are going to be 4 roots. We also know that the possible roots of any polynomial function would be the factors of the constant term over the factors of the leading coefficient. Constant term, leading coefficient. Now you don't have to worry about the negative because it's going to be plus and minus of everything. So we are taking the factors of 18 over the factors of 2. Factors of 18 would be 1, 2, 3, 6, 9, 18. And the factors of 2 would be 1 and 2. So then our possible roots would be plus and minus all of these things over 1 and all of these things over 2. So anything over 1 is just going to be it. So 1, 2, 3, 6, 9, 18. Then you can put all of those over 2. So then you would also add 1 half. 2 halves is 1, so we don't have to write it again. 3 halves, 6 halves is 3, so 9 halves. And 18 halves is 9. So there you have the possible roots. These are the only numbers that you would need to try in your L. Plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6, plus and minus 9, plus and minus 18, plus and minus a half, 3 halves, and 9 halves. So it takes infinite numbers to try down to a reasonable amount. Hopefully it doesn't take you too long to guess one of them. One other thing that you can do to narrow this list even is with Descartes' rule of signs. If we have a polynomial function and we are trying to find the roots for it, by our last rule, the rational zero test, we know that the possible rational roots are going to be the factors of 6 over the factors of 1. So that would be 1, 2, 3, and 6. Now, what will also help you is for every polynomial function that you have, the number of sign changes that a polynomial function has throughout it is equal to the number of positive roots in that polynomial function. And they have to differ by 2 each time. So, for example, this particular function here, if we want to know how many positive roots it has, all we have to do is count the number of sign changes. So from here to there is no sign change. From there to there is a sign change. Here to there, no sign change. And here to here, there is a sign change. So what that means then, because there are 2 sign changes, there are 2 possible positive roots right now. And because it can be differing by 2, there could also be zero roots that are positive. Okay? If you had 3 sign changes, then there could be 3 possible positive roots or 1 possible positive root. If you had 20 sign changes in the polynomial function, then you could have 20 possible positive roots. You could have 18, 16, 14, 12, 10, 8, 6, 4, or no positive roots, because it always has to differ by 2, starting with the largest one. You can also deal with the f of a negative x. If you substitute a negative x in for f of x, in this particular case, and so now simplifying this, a negative x to the fourth is x to the fourth. 8 times the negative x cubed. Negative x cubed is a negative x cubed times 8 would be minus 8x cubed. Negative x squared would be x squared. That still stays a negative 7x squared. And that would be plus 2x plus 6. Now we would look at the number of sign changes here. Changes from positive to negative, so that's 1. Negative to negative doesn't do anything, but negative to positive does, so that's 2. And then positive to positive isn't, so then there are 2 again. Now how does that help you when you're trying to figure out all of what the roots are? Well, if you have all of these and you know that there are no positives, then you can get rid of them. You don't have to try 2 out here, or 1, or 9 halves, because it tells us we don't have any. Finally, the last thing for this section deals with once you start doing your L thing and trying out different values for it and finding some things, there is an upper bound rule that you need to understand. And the upper bound rule states that if you have a positive number out here and you have your things on the inside, and when you go through this process of adding down and multiplying, if all values in this row all the values are positive, then the rational number that you just tried to divide by is an upper bound. By upper bound, I mean, then let's say you tried a 3 out here and we got all positives or zeros across here, because it could be a 0 also. So if you try a 3 out here and you get all positives or 0, then you know that 3 is the largest value you have to check, because nothing above 3 is going to work if that's the case. So looking back at that example where we had the possible rational roots for this at factors of 6 over factors of 1, well, if you did that, and you tried some number on the outside and say it's a 4, and you got values in here, then if this alternates, so like 3, 0, 5, negative 2, 6, that alternates because the 0 can become positive or negative. It's neutral, so it can go either way. And so that alternates. But we don't want it to alternate. That's right. We want it to be all positive here. So now, because these are all positive, 4 would be considered an upper bound. meaning no value above 4 you would have to try out here because none of them are going to work anyway. Then there's a thing called the lower bound. Same type of principle, except it is slightly different as far as what happens. The number on the outside, if it's going to be a lower bound, must be negative. What's different about it is when you do your thing, and you've got your values here, the bottom here has to alternate between positive and negative. If it does alternate between positive and negative, then that number that's negative here is a lower bound, meaning no number below that would have to be tried outside of here. So let's say you had some possible rational roots of plus and minus 1, 2, 3, 4, 6, and 12, and 18, and 36, and 9. Say those are all of your possible rational roots. Well, when you go through this process, say you tried a negative 2 out here, and now this part of it alternates, so like, let's say 0, 4, negative 2, 0, 5. Look at this as this being negative. Actually, this has to be a negative 5. That's positive. That's negative. 0 can be either, so we want that to be positive, and then a negative. Now, because it alternates back and forth between positive and negative, negative 2 is a lower bound. These two things, the upper bound and the lower bound, they are just things to help you with finding all of the possible rational roots. So as you're going through this, if you put a 4 out here and you get this, and then you go and try a 6 afterwards, then you're not very smart because you don't understand the upper bound principle. This is a 4 and these are all positive, then you don't have to try anything above 4. With a negative value, it has to be a negative on the outside, and then these all have to alternate. Whether it starts negative or positive does not matter, they just have to alternate. And that is everything from the third section of Chapter 2.